sky is blue is definitely an example of such a thing, because if you just look in the sky, you can't see any immediate reason why it should be blue, why it's, for example, not green or red or so. Yeah, so there are also other reasons why you can ask the questions, because if we then have a theory for the blueness of sky, then we can try to generalize it a bit and apply it in other circumstances. Like we can, for example, ask what the color of the sky is going to be when all the oxygen is replaced by carbon dioxide in the atmosphere of Earth, if all the global warming people are right. And then also we can use it, if we have the model, we can test the model, or to test whether the approximations in the model that I'm going to present are correct, whether they really predict the blueness of sky. But let's go to the actual physics. Yeah, so because we all know that color is really a manifestation of a property of light, which is wavelength, then and we know that all light that we can see around us, or almost all of it, comes from sun. We should first look at what the power spectrum of sun looks like, and it looks like this. You can see that the maximum of the maximum power is produced around the visible wavelengths, which is for quite a deep reason, or evolution reason, that our eyes really developed in such a way that we can see the range in which the power spectrum of sun is maximal. And but also all the colors are represented in approximately the same amount. There is a slight peak in the blue light, but it is not really big enough for the light which comes from the sun to look blue. So if we just look directly into the sun, it looks like this. It's completely white. Yeah. So what's the reason that the sky is blue? Well, it's because the light that comes from the sky doesn't come directly from the sun. It is light which originally comes from the sun, but then is scattered by the particles in the air. And air consists of mostly from the nitrogen and oxygen molecules, and there's also some argon and other things. And the important thing to note is that the size of the molecules of these things is quite small compared to the wavelength of light. So it's around 100 picometers, which is less than 1,000 of the typical wavelength of light. So we are going to use that in the approximation a bit later. So let me just say what the scattering means. It's very simple. You have some electromagnetic wave coming from the sun, and it wobbles with the particles because they are charged, the particles in the air. And these particles then, as they wobble, they are accelerated and they also radiate. So our task now will be to calculate what the power spectrum of the radiation produced by the particles is. Yeah. The model that we use is very simple. It's classical. So we just consider the molecules are charged harmonic oscillators with some natural frequency omega 0 squared, or omega 0. And we apply the electric field. Just forget about the magnetic field because it has the same behavior, and which varies harmonically. Omega is the frequency of the light at the particular frequency. Then we can just use the complex exponential formalism and derive the relationship between the position of the atom in the molecule, or of the molecule, and depending on the electric field. And from this, the important quantity that we need to find is the average acceleration over one period. So, yeah, the way we derive this is, well, this is derived immediately just by substitution for x of a form something times e to the I omega t. And then if we differentiate this twice with respect to time and average over one period, differentiation brings in the factor omega squared. After squaring, we get omega to the 4, and 1 over 2 is the average over one period. Yeah. Now if we want to calculate the we use the approximation called the Rayleigh scattering, which is the approximation which I have already mentioned, and that is that the size of the molecules is much smaller than the size of the wavelength of light. So actually, in our setting, it means that the natural frequency of the harmonic oscillator is much, much bigger than the frequency of the light, because if the frequency is high, it means that the molecule is tightly bound, which means it's small. And this is exactly the relationship to which it translates in our variables. Then if we just substitute, if we use this approximation and use the Larmore's formula for radiated power, which relates which tells us how much power a charge of magnitude q radiates if it moves at acceleration a. And we use that approximation, so we just substitute for a from here, but we can neglect the omega squared in the denominator and just consider omega 0 squared, because omega 0 is much bigger than omega. We get this. So you can see, it is not surprising that the power is proportional to E squared, because that's the intensity. But the most important thing is that it is proportional to omega over omega 0 4 to the 4. So if we now express this proportionality in terms of the wavelength, you see that the radiated power at a particular frequency of the light, the incident light, is proportional to 1 over lambda to the 4, which means that the short wavelengths, i.e. blue wavelengths, are scattered much more than the red wavelengths. So this is basically the reason why the sky is blue. And we can bring this argument even further and ask the question why during the sunset sky is red. Well, the explanation is now very simple, because we know if the sun is really low nearby the horizon, in this picture the sun is actually below the horizon already. All the blue light has been scattered away, and all that we see is the red light, which remains from the original blue light coming from the sun. And so yeah, here's a nice picture where you can see how the blue color coming from parts of the atmosphere where the layer of atmosphere is not so thick merges into the red color in parts of the atmosphere where the layer of atmosphere between the sun and us is much thicker. So more blue light has been scattered away here than here. And this is another example of Rayleigh scattering. It's a piece of glass with some nanoporous structure where we can use the same approximation, and also it looks blue. And you can see that the light that passes through it and hits the desk is orange or is red. So it's exactly the same principle. Okay, yeah, because I still have some time, I'm going to also tell you why the clouds are white. In fact, these are two related questions, or one question in the other. The first question is why there are clouds, or why we can see clouds. Because it is not so natural, because as we know, the clouds consist of water vapor, which is condensed, but the water vapor is in the air already before it condenses. So why don't we see the water vapor before it condenses? Well, the reason essentially is that when the water molecules condense, they get close to each other, and then we can see some sort of constructive interference, because if they are close, if two molecules of water are closer to each other than the wavelength of light, then the electric field which comes from them adds up constructively, coherently, which means that the magnitude, the intensity, scales with the second power of the number of molecules, rather than with the first power. So if we have a droplet which is smaller than the wavelength of light, where there are, say n molecules. If we have a droplet where there are n molecules, then if it's small, we get coherent interference, or coherence. So the intensity is proportional to n squared. Whereas if we have just scattered loads of molecules which are not so close by, the intensity is just proportional to n. So that's the reason why we can see the water only after it condenses. Yeah, this whole mechanism works only until the droplet size is smaller than lambda, because the droplets grow, and at some point they reach the size lambda, and then this enhancement is no longer becoming better and better. But we can also use this to explain why the clouds are not blue but white, which is essentially because the red light has greater frequency, which means that larger water droplets are allowed to contribute using this n squared enhancement than for the blue light. So even though blue light is scattered more, there will be the larger droplets have this n squared enhancement for the red light. So these two effects compensate for each other, and we can the light which is coming from the clouds is actually white because both blue and red are enhanced in the same way. In the end, there are some improvements which we can make to our theory. So we can consider instead of Rayleigh scattering the Mie scattering, which is also applicable when the size of the molecules is finite, not zero. And we could also consider a more realistic model for the molecule, quantum mechanical, but not really necessary because we already can see that that we have explained the blueness of sky using our very simple model. So not a big need for improvements here. And we can also consider what happens to the polarization of light. That's also an interesting problem to see, like from which parts of the sky we get what sort of polarization. Thank you. Mm-hmm. How is it that we don't see green? So it is not. This is not really. What's it called? It is not a refraction of light. So it's not the same situation as if when you have a prism and the white line shines through it. This is just that. Well, the reason why this is blue and this is red is that blue is scattered more. So here you can see the scattered light, but here you can see the light which passes through. And the light which passes through doesn't have any blue light because the blue light has been scattered away. And exactly in which part of the spectrum is green? Is it somewhere in the middle?
Close to, that's actually close to blue.
It's close to blue.
Closer to blue than red.
Closer to blue.
I have to say that actually green flashes exist. They're very rare even, but exist.
It's also would be possible if you're removing blue from the spectrum, the combination of the others would appear more red, right?
Mm-hmm.
The yellow interface.
Yeah. I would say it's really quite a complex question how all the different things overlap, and also the complex issue is the interpretation of color by the eyes, because it's not really like that. Our eyes just can see the wavelength and then they tell you what the color is, because they can. If you compose two different wavelengths, it looks like a different color. It's quite a complex issue.
Don't you have